Hello, everyone, and welcome back to class. This is Dr. Dax. We are in week 2 of your fundamental classification techniques class. This is the first session of the week. I hope that everyone out there has had a good weekend and that everybody in your home is happy and safe and doing well. And what I want to do today is we're going to begin talking about some of the classification techniques that we're interested in, starting off with the K nearest neighbors. And before we dive into that too much, I want to refresh your memory on KNN. And before I do that, though, let me share contact info. I want to get that out of the way. This is my email address. If you have any questions or suggestions or anything you want to see, email me at that address on your screen. It's also on the profile page. Additionally, you can contact me through texting or calling me. That information is on the syllabus. So if you need anything at all, shoot me a message. I'll get back to you within 24 hours. All right. With that being said, I was going to describe what we're looking at, KNN. Okay, so your first module is going to deal with K nearest neighbors. It's a form of classification that specifically deals with supervised material. Now, if you're dealing with an unsupervised data set, you might be looking at K-means classification. And this is all different from regression because in classification, we're interested in classifying a specific discrete outcome. Or in the case of K-means distribution, we're probably looking at a description of the probability of an outcome. In regression, we're not dealing with a supervised data set with a specific discrete outcome. We're looking at something over an extended period, and we're looking at a prediction. All right, so before we get too much further, let's go ahead and dive into the PowerPoint. I want to get that pulled up, and hopefully it's working. You should be able to see that. So today, we're talking about cluster analysis. That'll form the basis of your study for deliverable 1. Our objectives are pretty simple. We're going to discuss classification and what that means. We'll describe clusters of features in high dimensional space. I want to define the difference between supervised and unsupervised learning. We'll cover the K nearest neighbors approach and touch lightly on K-means clustering. So my goal for you is basically to be able to describe the importance of clustering in classification. And hopefully we'll have time to see the example of K-means clustering. And you're going to be able to think critically about feature types and how they're helpful and what should be discarded. So the first thing we do with our data set is we need to define the problem. We will say that given a set of data points, we're going to group them into clusters so that points within each cluster are similar to each other. Points from different clusters are dissimilar. So usually, points are in a high dimensional space, and similarity is measured by using some distance measure. And that could be Euclidean distance, cosine, Jacquard, edit distance. It could be absolute. The coordinates could be polar, and so on and so on. So when we're describing high dimensional space, all that means is we're not just dealing with 2 features. We have a data set with many features often. And in dealing with a high dimensional space, we're going to create a series of clusters to put features that belong in a group together. Let's take a look at an example that's kind of simplistic, but sort of drives home the point. Let's say we have a set of elements with different features, and these different features describe various element attributes. And we want to use those element attributes in order to predict what kind of dog we're looking at. And we might have a group of elements that belong in this cluster here, another group in this cluster over here, and a third cluster here. Now, in this example, it's fairly simple. We've got 3 distinct clusters based upon 2 features, height and weight. And we might be able to predict that the lowest weight and height is probably Chihuahuas, and the next group is Dachshunds, and maybe the third group has a little bit more height and slightly more weight. It's probably Beagles. Now, of those 3, if you have a height and weight, you should be able to predict what cluster they fall into. Now, again, this is not an exact study. This is hypothetical just for illustrative purposes. Obviously, there are a lot more types of dogs out there and a lot greater closeness in features, but that's just to give you a look at what we mean by clustering. Other forms of clustering can be used for many different purposes. We can place customers into groups based upon their purchase histories. If you're dealing in retail, that could be easy to do if you're using web analytics tools to track the purchasing histories and describe how much money they spend, what items they're buying, where they're buying them from. Additionally, we can cluster products based upon the sets of customers who purchase them, taking that information that we used in the purchase histories and extrapolating what products are the most popular, what are the least popular. Additionally, you can cluster documents based on similar words, and you can cluster DNA sequences based upon edit distance and so on. And the list goes on and on. There's many different ways we could use clustering. It's one of the most popular and commonly used forms of machine learning. Remember that clustering is a form of unsupervised learning. So, for example, we could say, given that only x sub I in that data set of I equals 1 up to some number n, can we infer the underlying structure of X? So the point of it is to basically discover groups that are established in such a way that the samples within the group are more similar to each other than samples in the other groups. And if so, is it possible to distinguish those groups and cluster them accordingly? So in this example, we made it easier by color coordinating the clusters. Here we can see 3 distinct groups. So we've talked a little bit about supervised and unsupervised clustering. Let's describe some of the differences here we're looking at. In supervised learning, we're dealing with data that is trained from labeled samples. We know exactly what they are, whether they're continuous, discrete, categorical, or what have you. They're labeled clearly. Essentially, they're already tagged with whatever they are. In other words, the quote-unquote correct answer. The algorithm learns from labeled training data to help predict outcomes. In unsupervised learning, we're dealing with data that is unlabeled. Now, recall from earlier studies that unlabeled data can be anything that is continuous, intrinsic in nature. Maybe it's audio, maybe it's video, maybe it's a lot of emails, text. And unsupervised learning is suitable for more complex tasks. And it can be somewhat unpredictable. So why supervised learning? Supervised learning allows us to collect data or produce data output from previous experience. It helps you to optimize performances using historic data. From that experience, we can interpolate what is the predicted outcome. Supervised machine learning helps us to solve problems of various types in real-world computational situations. Unsupervised learning differs because the raw data is cheap, whereas labeled data tends to be expensive in terms of resources, storage costs, time allowed to perform the predictions. Raw data in unsupervised learning is cheap because it's so readily available and there's so much of it. Unsupervised learning, rather, helps to reduce the noise in high-dimensional data. It forms the basis of a methodology to eliminate redundancies, outliers, extreme data on either side, and it's useful in exploratory data analysis, or EDA. Often, unsupervised learning provides us pre-processing steps for supervised learning. So I want to pause here and remind you that in a data study, it's not uncommon for the various classification tools to overlap. We talk about unsupervised and supervised learning, and we also talk about taking data through k-nearest neighbors, which is considered a supervised learning, but it might form the basis of a k-means cluster study, which is considered unsupervised. So don't be surprised if you're using techniques from both camps within the same study to answer your questions. In the k-nearest neighbor machine learning tools, we're interested, we just talked about KNN. In KNN, k-nearest neighbor, that's supervised learning, which basically involves us trying to identify elements by the distance to the centroid of the next cluster over. So you might choose a k value of, say, 3 or 4. And with that, we can take an unknown element, measure the distance to the centroid of a cluster, and we can say it's closer to 3 or 4 items of that cluster than the other cluster. So what cluster is it? We classify it by the number of the k that's the highest. K-means assumes Euclidean space, and we start by picking the number of clusters rather than the number of elements in the cluster. And we initialize clusters by picking 1 point per cluster. And this is done automatically in Python libraries. So while there are formulas that can go into fairly complex calculation, it's done automatically. And we can use parametric and non-parametric techniques. Now, non-parametric techniques involves density estimation, and we can use P of x equals the k value divided by NV, where k is the number of samples and n is the total number of samples, and v is the volume surrounding x. Basically, we're interested in 2 approaches to the estimator. Parse-in window approach is done by fixing the volume v and determining the number of k of data points inside the volume. K-nearest neighbor, or the KNN approach, which is what we're going to be spending more time on, is fixing the value of k and determining the minimum volume v encompassing those k points. There are advantages and disadvantages to this non-parametric approach. Advantages to non-parametric techniques is, well, there's no assumption about the distribution required ahead of time, so it's considered to be distribution free. And if you have enough samples, we can converge it to a target density. So pre-analysis, generally speaking, is not required. Whereas disadvantages are if we have a good classifier, the number of required samples might be fairly substantial. That means it's going to be computationally expensive in terms of resources and computing power, time, and other resources. So let's talk a little bit about the k-nearest neighbor rule. Basically, the KNN classifies unlabeled examples based upon their similarity with examples in the training set. There are some requirements. It requires some integer k. It requires a set of labeled examples and a metric to measure the closeness. And the metric has to be consistent and has to be repeatable. Let's take a look at an example. Let's say we have 3 classes, and the goal is to find a class label for some unknown sample that we're going to call X sub u. There's 3 different samples there are labeled omega 1, omega 2, and omega 3. How do we determine what group it falls into? Well, in KNN, we're going to use Euclidean distance, and we'll give it a value of k equals 5 neighbors. So we pick the 5 closest elements, and we determined that 4 of those elements belong to omega 1, and 1 of them belongs to omega 3. So, based upon that, X sub u is assigned to omega 1, the most predominant class. Why is it the most predominant? Because more of the elements there fell within the Euclidean distance of k equals 5. 4 out of 5, in fact. So with 80% probability, we can say it's a omega 1. So we've been tossing around the idea of using the k value, but how do we get k correct? What is the best methodology to determine that? Is it arbitrary? Is there a calculation? Well, what we can do in KNN is try different k values, looking for a change in the average distance to the centroid. And what we find is that it will typically fall rapidly right after the nominal value of k. Alternatively, you can run checks on the accuracy value and determine the optimum value of k. So you run repeated efforts, k equals 1, k equals 2, k equals 3, k equals 4, and so on, and observe the drop in accuracy. Once it drops, it's the k right before that. Now, k-means is quite advantageous, but it's not perfect. Some disadvantages include the idea that you must know in advance the optimum number of clusters for the k value. And it can be particularly sensitive to outliers. So data cleanup is absolutely important. And reordering of the data may affect the results. Also, it requires vast memory sometimes. And note that hierarchical clustering is a potential alternative. So in k-means clusters, we can determine by using a dendrogram the optimum number of clusters. And we'll talk more about that later on in the class. So that's the basic rundown of k-nearest neighbor operation. I hope that you found that somewhat useful. What I'm going to do at this time is I'm going to try to pause, and I'm going to pull up an example of KNN, which you can hopefully apply to your studies. All right, so what I want to do is take a look at one method we could use to find the best k value using a data set that's not the same one you're going to be doing your homework in. I just want to give an example. So if you take a look here in this notepad, I've got Telecustomers pulled up. That's a data set you can pull up, and I can share this with you. It's got the resource link in the comments where you can get this data set, but hopefully you can take advantage of that. And what I'll be doing is dropping this code into Python. So first I want to use itertools, numpy, matplotlib, pandas, numpy, and sklearn. Let's jump over to Python and drop that in. All right. Next thing I'm interested in is pulling the data set in. I'm going to call it data. And I need to go ahead and fix the path here. And let's take a look at the head. All right, so we can see that we got the region, tenure, age, marital status. We do have a final category. That's our target. Looks like customer category 1 through 4. And the actual file looks like this. Got that pulled up. Next part we're interested in is doing our value counts. So we can see that we have 281 category 3, 266 of category 1, 236 of category 4, 217 of category 2. And we can go ahead and drop customer category. So I'm going to do X equals data.drop. And let's do a head and see what it looks like. So now we can see that that column is gone. All right, what else can we do? We can set up our Y as the customer category. And now I want to set up the test and train split. Show you what that looks like. To go from sklearn model, test train split, and we use a random state of 4. I'm going to do an 80-20 split. And next up, we want to import k nearest neighbors classifier. And I'm going to set an arbitrary k value of 4. Just see how that turns out. All right, now we're going to train the model and predict. And we will check the accuracy. Accuracy is 0.26. Not too good. Let's run the prediction Y. All right, there's our predictions. Next up, let's set the number of Ks to 40. And what we're going to do is we're going to iterate 1 to 40. Next up, we're going to plot it out. And let's see if I can get that to show you what it looks like. All right, so you got the error rate versus the K value. Now, if we look here across the K values from 0 to 40, well, 1 to 40, 0 to 39, the error rate was the highest at about 4. It dropped way low over here at around 37, perhaps. Let's go back to the code. That's the that methodology was just taking a look at the output and visually trying to see where the best value for K is. Here I'm guessing around 37, 38, but we can do another check by going over the accuracy. So let's take a look at the accuracy. That's the next part. And we can go ahead and print the accuracy out. Maximum accuracy was 0.375 at K was 38. So the highest accuracy rating was at K is 38. I said it was around 37. So that's pretty much in agreement with the image that we had. So that is one method of obtaining the appropriate number for K and K nearest neighbors. And I'll share that code with you in the uploads. And I hope that's useful to you and interesting. All right. So basically, that was a basic rundown of our K nearest neighbors classification. Remember that it's different from K-means clustering, but sometimes in a larger study, it's not impossible to have to use both. But for the purpose of deliverable 1, we'll be doing KNN, and we'll talk more about that on Thursday when we meet next time. If you have any questions or concerns, shoot me a message to dax.bradley@rasmussen.edu, and I hope this has been valuable to you to help you get you going on deliverable 1 and forward from there. And this is really the heart of what we're studying in this course, classification. We're very interested in forming predictions based on historic data and probabilities. So it's really interesting to me. This is my favorite class to teach, and I really enjoy getting into this part, the nuts and bolts of it, and sharing the code with you. If you come up with different solutions that are vastly different from what I've got, don't be afraid to use them. Share them with me, and as I see stuff that I find interesting, I'll share it with future students. It's all good. And if there's anything you need, let me know. I hope that this has been good for you. I'll see you in a couple of days on Thursday. And just a quick reminder, going forward, I'm going to be recording these classes during the daytime, 10 o'clock Central Time in the morning, 11 o'clock Eastern Time, due to scheduling constraints at my day job. So that is why we're pre-recording now. And if that's not working out for you, let me know. We'll try to figure something out. But I think for now, it's the best way to go. That's it for now. I'm Dr. Dax. I've enjoyed it. I'll see you again soon. Take care.